Okay, here is an example question about energy. And I picked this one because it's not in the homework and it gives me a chance to review force analysis, which was a big part of the previous 7 weeks of our course between exam 1 and exam 2. So this was from the additional problems in chapter 7, or just, I'm sorry, chapter 5, or do they call it topic 5? And we have this block that is pushed up a vertical wall with constant speed by a constant force. And the force is diagonal, as shown in the figure down here. And we have a coefficient of kinetic friction determined by blah. Determined the work by a bunch of things. By the force, by friction, by gravity, etc. So where is my pen? There it is. So the first thing I have to think about is what forces are affecting the block. And this is usually not a written process. This is usually a thought process, a mental process. And we definitely have gravity, which is our distance force. And we definitely have the applied force, which I'm going to call F of pushing. I don't like to use a generic variable for a specific quantity because a plain F could mean any force. And if I appropriate that name for a specific force in an example, then I no longer have the freedom to use it to mean any old force, and I like to keep that. So I'm going to call that F sub P and draw F sub P, F sub P, sub P. And then there's also the contact force, and with a friction case, we always split the contact force into 2 parts. And we call them the normal force and the friction force. I usually just call the friction force F sub F for friction. Our textbook has this tendency to call it little f vector subscript k to remind us it's kinetic friction. So then the next thing we want to do is we want to think about the directions of all these forces. So we need a free body diagram. So in our free body diagram, we're going to have our object, and we're going to have to scroll back and forth a little bit, but we'll have our downward away. F sub G. And the next one that's fairly easy is this pushing force, F sub P. And then the normal force always is perpendicular to the surface. So it's going to be pushing the block toward the left. So it's going to be pushing away from the wall, F sub N. And then we have this little conundrum. The friction force could be up or down. And we have to decide which way it is. And in this case, the block is moving upward. It is being pushed up. So that is an active verb that's saying that something is actually happening. So, so kinetic friction has to oppose this. So that means that we have our F sub F, which is down. So that's a good next step in our analysis. And at this point, we should take a tally of which forces we know, which forces we don't know. We know the gravity force. So that's the gravity on a 5 kilogram block. So we can say that the force of gravity is 5 kilograms times 9.8 newtons per kilogram. And as I recall, that comes out to 49 newtons. So this is 49 newtons. So that's nice. Is there anything else we know? We know this constant speed thing. Well, that's pretty significant. So let's make note of that. This block is moving with a constant speed in a constant direction. So that means that the acceleration of the block is 0. And that means when we go to do Newton's second law, our forces must balance, both x and y direction forces. So let's see what we get in the two directions. I need to add one more thing to this diagram. Actually, I want to make that a dash line. We're going to go dash, 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 dash. 30 degrees. So we need to do an equation for the x direction and another equation for the y direction. And in the x direction, we have, I'm just going to temporarily call it fpx, and minus fn equals 0. So we only have two forces that are not vertical forces. So they have a horizontal component, they have an x component. So I symbolically put them together. And in the y direction, I have my Fpy and minus the force of friction and minus the force of gravity equals 0. So I've written both of my force balance equations, and now I have to figure out how to split that pushing force into components. So this is something that would sometimes happen very quickly, but since I'm doing everything out in full detail, I'm going to show it. So we have this force that is pushing upward and to the right. And in the original diagram, it's upward and to the right. In my free body diagram, it's upward and to the right. But now I'm drawing just a set of x-y axes for the force so that I can divide it into components. And when I do that, I see that the 30-degree angle is part of a triangle. Here is FPX, here is FPY, and here is FP. So that tells me that that diagram is what tells me that the x component is adjacent to the 30-degree angle. Now we could see that from the original diagram. We can see the angles measured to the horizontal. So that's always going to make that angle adjacent to the x component. We can see it here in the free body diagram, and we can see it in this little diagram for just the force vector. And then we need two additional things if we're doing triangle trig to find vector components. We need to say that the vector is to the right, so fpx is positive, and if those aren't words, they are now. The vector is uppish, so the y component is positive. So now these equations turn into fp cosine 30 degrees minus fn equals 0. And fp sine 30 degrees minus ff minus, actually, let's plug in a known number for the force of gravity, 49 newtons equals 0. All right. So at this point, we have a bit of a problem. We have two equations and 3 unknowns. And just to take a tally of them, my unknowns are the normal force, the friction force, and the pushing force. Even though I didn't know the strength of the pushing force because it wasn't told to me, I have managed to take two variables, the x component and the y component, and reduce them down to one variable, just the magnitude of the pushing force. And the magnitude times the cosine is the x component, the magnitude times the sine is the y component. So this process here brought me from 4 variables down to 3. Now I need to figure out how to get from 3 variables down to 2 because I only have 2 equations. And then what equation am I going to use in order to figure out one more link? The additional equation is the kinetic friction. So we're going to have force of friction is equal to mu kinetic times the normal force. And we were told a mu kinetic of 0.3. So the force of friction is equal to 0.3 times the normal force. So now I have 3 equations. We have 1, 2, 3 equations. I know that's not very readable, but so we'll try plugging things together. Now we're at the point of doing some ugly algebra. Actually, we're going to plug 3 into 2. So now equation 2 is going to be fp sine 30 degrees minus 0.3 fn minus 49 equals 0. Now we have two equations and two unknowns. So we can plug one in. One tells me that Fn equals Fp cosine 30 degrees. So let's plug that in. Fp sine 30 degrees so Fp sine 30 degrees minus 0.3 Fp cosine 30 degrees minus 49 equals 0. Now I have an equation with only one variable. So now I can find my Fp times sine 30 degrees minus 0.3 cosine 30 degrees equals 49. And I might as well calculate this thing in parentheses as a number. Notice I had two terms with Fp. So I factored the Fp out, and I'm left with whatever coefficients, whatever multipliers were in front of the Fp. So now I'm just going to calculate this real quick on my calculator. Sine 30 minus 0.3 times cosine 30. 0.2402. So now I can just take my 49 newtons and divide it by that answer. So I'm going to hit 49 divided by answer equals 0.04. And that's what breaks everything open in this analysis. Now I know, and I can even make note that Fp equals 204 newtons, or up here, 204 newtons. And it was like 204.00 in this particular case on my calculator. So now what do? Now I need to find those other two forces. Because I started a force analysis, I might as well finish my force analysis. So we have Fn equals 204, oops, not sine, cosine 30 degrees. So that's from up here. (176.7). And then the force of friction is equal to 0.3 times 176.7. So I just go times 0.3 equals 53.0. 53 newtons. So now we know that this is 53 and this is 176.7 newtons. Whew, that was my force analysis. All complete, all explained out. And I am recording this so you can go back over it later and see what I said and review it. Now, what is the actual question? We want to know the work done by each of these forces. Work. So what I want is the free body diagram. I'm going to try to copy that so that I can take it down. All right, that seems to be what I want. There we go. There's my free body diagram. Actually, let me move this stuff over here. So now we need the new topic, calculating work due to forces. And I pointed you to the notes and the lessons from last year. I did a very brief introduction, conceptual introduction to energy on Monday, but work is equal to, for example, Fx delta x. And that applies for cases of horizontal motion. We could also do a change of coordinates. Work is also Fy delta y. For vertical motion. And in this case, we know the delta y. We know that this object is getting pushed 3 meters up the wall. So let me make note of that. Delta y is equal to plus 3.0 meters. So now to calculate the work due to each force, all I have to do is to think about the force, find its y component, for instance, the pushing force, and I can use that to calculate the work. So let's do FP. I would call that work due to the pushing force is FPY delta y. And FPY, we up here did our equations of motion. FPY was this thing, FP sine of 30. So I'm just going to write that there, FP sine of 30 degrees delta y. And now I'll plug in all my numbers. My FP was 204 newtons sine 30 degrees. My delta y is 3.0 meters. And I get 204 times sine 30 times 3 equals 306. 306, and we call them joules. And as a little side comment, when you're calculating amounts of energy and you're multiplying newtons times meters, always use joules for energy. Don't call them newton meters. Okay, so that was good. What other forces do we have? What else were we at? It's the force of gravity. So we have the work due to gravity is the force of gravity, y component, delta y, and we know the y component is just minus the magnitude because it's a downward force, so the y component is negative. And this was minus 49 newtons, 3.0 meters equals 49 times 3 equals 147 joules. Okay, the normal force. The normal force. The normal force is y component delta y. Guess what? The normal force is horizontal. horizontal force has only X force. So we seem to have this word. We seem to have an imbalance. We have work due to the pushing force is 306 joules. That is energy going into our object. And the work due to gravity is negative 147 joules. So our so 6 plus negative 147 equal to 159. So far, it looks like more energy is coming in than is going out. The object has constant velocity. It should have network is delta K E. K E kinetic energy calculated as 1/2 mv squared. So um, our crisis here, our dilemma is that the delta KE 0 and the network looks like 159. And that would break this equation. You can't have 159 equal 0. But the issue that happened here is we missed the force. We have friction. The work friction is force of friction, y component, delta y, numeric formula. And we know the force of friction is down, so it's negative, delta y. And we know how much friction we have. How much friction we have? 53. So minus 53 meters minus 1. Total now is network is work pushing plus work due to gravity plus work due to normal force. So network is work due to pushing plus work due to gravity plus normal plus work. The pushing force was 306 joules. Gravity was minus 147 joules plus 0 for the normal force plus 159. And there were a couple of important conceptual ideas so far. Um, the work due to the normal force equals zero. That happens a lot in our energy analysis, where the normal force doesn't affect the balance of energy. And that happened because force perpendicular to motion causes and another important thing that I tried to stress, the constant velocity situation has no, so that means say E some constant. I don't know necessarily what it is, but I know whatever it is, it doesn't change. There's no like initial final values. Is, and that means delta K E zero net work. So that means there has to be a balance of energy. So we're almost done with this example. It asked one more thing, by how much does gravitational, and I'm just going to do this part up here. So due to gravity, mgy delta p gravity delta y. So this is something that's in the lessons and talked about a little bit. So we can calculate this really quick. Have our 5.0 kilograms per kilogram times is 49 newtons. Did that already. And that's a positive 147 joules. So let's look and see how that's related to numbers we did. We have this positive 147 joules. So that 147 joules is this number here, negative 140. So the work due to gravity is minus they're opposite to each other. And the thing I want to point out here is that potential energy is an alternative way of accounting for the energy of some forces. And gravity is a force that. So we have our version 1 of this is this equation. Where we calculate the gravity's energy as work, and then that is what does this look like if we change to um, if we count for gravity's energy as energy instead of work, then it's called non-conservative work, and the pushing force would count. Normal force doesn't do anything, but it kind of counts. And the work due to friction counts, and that is equal to AE plus. So in a sense, we've taken this work due to gravity and subtracted it over to the other side of the equation and called it PE instead. So that is basically what happens when we're trying to figure out the relationship between energy and work for the exact same force. They are definitely. So that is my new and different example, and I'm going to close off this recording. That on YouTube. Eventually, I have to wait for WebAssign to process it, and then for me to process it to get all your names off the top.